He spent his life building our picture of the universe. It won him the Nobel Prize. Now he says that picture may be wrong. Adam Riess, the man who discovered that the cosmos is flying apart faster and faster, has found something he cannot explain. Two measurements of the universe give two different answers, and the most powerful telescope ever built just confirmed that neither one is a mistake. Tonight we follow the cracks he found, a force that may be fading, galaxies that formed too soon, a cosmic map that might be lopsided. If this journey pulls you in, a like and a subscribe help more curious minds find it. Now settle in, turn off the lights, and question everything you have ever known. In a quiet office at Johns Hopkins University in Baltimore, a Nobel Prize winner is staring at numbers that should not exist. His name is Adam Riess, and he won the Nobel Prize in Physics in 2011. The theory he is now questioning is the one his own discovery helped to build. This is confirmed fact, documented in interviews and published research. Riess is one of the most decorated scientists alive. In 2011, he shared the Nobel Prize in Physics for revealing that the universe is expanding faster and faster, a discovery so shocking that it rewrote every textbook on the shelf. That discovery became a cornerstone of the standard model of cosmology, the master blueprint describing how our universe was born, how it grew, and how it will one day end. Riess helped pour the foundation of that blueprint. He should be its proudest defender. Instead, he has become its loudest critic. For more than a decade, he has been measuring the universe with a precision no human has ever achieved. The deeper he measures, the stranger the answers become. He has said openly that something smells wrong with the standard model, that the numbers coming back from the sky refuse to match the numbers the theory demands. Think about what that means. Imagine an architect who designed a skyscraper, won every award for it, and then years later discovered a crack running through the building's core. Most people would look away. Riess walked straight toward the crack. Colleagues describe him as relentless, even combative, a scientist who argues fiercely with anyone who dismisses his data. Some senior researchers believe he is getting ahead of himself, that the discrepancy will dissolve with better instruments. That is their honest position, and it deserves respect. But Riess has spent years trying to make his own result go away. He has tested it, stress-tested it, and handed it to rivals, hoping they would find his mistake. No one has. The standard model does more than describe the universe. It predicts the fate of everything across trillions of years. If the model is wrong, the story of how everything ends is also wrong. The ending we were promised, a slow fade into cold and silent darkness, might be a fiction. Riess himself has admitted a haunting thought that he has shared in interviews and public lectures. He sometimes feels he is simply gathering clues, killing time, waiting for the next Einstein to arrive and make sense of it all. A Nobel laureate, one of the sharpest minds in physics, openly saying the answer may require a genius who has not been born yet. That is how deep this mystery goes. To understand how we arrived at this moment, we have to go back to a night in the late 1990s when a young Riess ran a calculation that made no sense. A calculation that said the universe was doing something every physicist believed was impossible. What he found that night did more than win him a Nobel Prize. It planted the seed of the very crisis that now threatens to bring the whole model down. Picture a young astronomer hunched over a computer in the dark, checking the same calculation for the 10th time. He was studying distant exploding stars called supernovae. His numbers were telling him something absurd. At the time, every scientist agreed on one simple idea. The universe was born in the Big Bang. It has been expanding ever since, and gravity has been slowing that expansion down, the way Earth's pull slows a ball thrown into the air. The only real question was how much it was slowing. That is what Riess and his team set out to measure. Their tools were a special kind of exploding star, a type of supernova that always detonates with almost exactly the same brightness. Astronomers call them standard candles because their true brightness is known and their distance can be calculated from how faint they appear, the way you can judge how far away a car is at night by the dimness of its headlights. Riess measured dozens of these cosmic explosions, some so remote that their light had travelled for billions of years before reaching his telescope. Then he compared their distances to the speed at which they were racing away. The expansion was supposed to be slowing down. His data said it was speeding up. He assumed he had made an error, a sign flipped somewhere, a bug in the code. He tore the analysis apart, looking for the mistake. It refused to appear. Meanwhile, a rival team led by Saul Perlmutter was performing the same measurement independently using different supernovae and different methods. They found the same impossible answer. Two competing teams racing each other arrived at the same forbidden result. The universe is accelerating. Something is pushing every galaxy away from every other galaxy harder and harder, with a strength that grows as space itself grows. Scientists gave this unknown force a placeholder name, dark energy. Imagine tossing a baseball into the sky and watching it slow, hover, and then suddenly rocket upward into the clouds, faster every second, as if the sky itself had grabbed it. That is what the universe was doing with entire galaxies. The discovery landed like an earthquake. Within years, it was confirmed by independent observations. In 2011, Riess, Perlmutter and Brian Schmidt shared the Nobel Prize in Physics. Dark energy was written into the equations of cosmology and became a pillar of the Standard Model. But notice something unsettling. The pillar is made of mystery. No experiment has ever revealed what dark energy actually is. Physics has a name for it and nothing more. When Riess and his colleagues added up the cosmic inventory, the results were humbling beyond words. The acceleration implied that this unknown force dominates the universe, outweighing everything we can see by an enormous margin. Hold out your hand and look at it. Skin, bone, blood, atoms forged inside ancient stars. Everything made of atoms, your hand, this planet, our sun, every galaxy ever photographed, adds up to only about 5% of the universe. The other 95% is invisible. It has never been touched, captured, or directly detected by any instrument ever built. Scientists divide that hidden majority into two parts. Roughly a quarter of the cosmos is something called dark matter, an unseen substance whose gravity holds galaxies together. We know it is there because galaxies spin so fast that without some hidden mass gripping them, they would fling their stars into the void like water off a spinning wheel. Something keeps them whole. That something outweighs all visible matter about 5 times over, yet it emits no light, no heat, no signal of any kind. The rest of the hidden universe, roughly 70% of everything, is dark energy, the mysterious push that Riess helped discover. It does the opposite of dark matter. Instead of pulling things together, it drives space itself apart. Try to picture the imbalance. Imagine the entire universe as a large pizza cut into 20 slices. Everything astronomy has ever shown you, every glittering photograph from every telescope in history, fits on a single slice. The other 19 slices are dark, unknown, and unexplained. That is the actual situation of human knowledge tonight. The existence of these dark components is strongly supported by many independent observations. That part is solid science. but their identity remains a complete unknown. Physicists have hunted dark matter for decades with giant detectors buried deep underground, tanks of liquid cooled to extreme temperatures, waiting for a single invisible particle to bump into an atom. The detectors have grown ever more sensitive. The silence has remained total. Dark energy is even more slippery. It appears to be a property of empty space itself, as if nothingness carries a hidden charge that pushes outward. When physicists tried to calculate how strong that push should be using quantum theory, their answer missed the observed value by a factor so colossal that it has been called the worst prediction in the history of physics. The theory and the measurement disagree by more than a 1 followed by 120 zeros. Our best theory of matter and our best theory of the cosmos, when asked the same question, give answers separated by an abyss wider than imagination. Now understand why this matters for our story. The standard model of cosmology is built on top of these two mysteries. It assumes dark matter behaves in a particular simple way. It assumes dark energy is perfectly constant, never changing from the first moment of time until the last. These assumptions work astonishingly well. They allow the model to fit thousands of observations. But an assumption is a promise waiting to be tested, and Riess spent his career building the tools capable of testing it. For years, the model passed every exam it was given. It seemed untouchable, a theory of everything cosmic, which makes what happened next all the more remarkable because the first serious crack appeared in the exact place Riess knows better than any human alive. Before we watch it crack, you deserve to know what the standard model actually is and why scientists trusted it so completely. Think of it as the biography of the universe written in mathematics. It begins nearly 14 billion years ago with the Big Bang, an unimaginably hot and dense beginning. In the first fraction of a second, space itself inflated with violent speed, smoothing the cosmos like a wrinkled sheet snapped flat. As everything cooled, particles formed, then atoms. Then the first light broke free and has been traveling ever since. Gravity gathered matter into webs and knots. Those knots ignited into stars. Stars gathered into galaxies. Galaxies gathered into clusters strung along invisible filaments of dark matter, forming a cosmic web that spans everything we can see. The model needs only a handful of ingredients to tell this entire story. A pinch of ordinary matter, a generous helping of dark matter, a dominant portion of dark energy assumed to be constant forever. Feed those ingredients into the equations of Einstein's gravity, and the universe unfolds on a computer screen almost exactly as telescopes observe it. The successes are genuinely staggering, and this part is confirmed science backed by decades of cross-checking from independent teams using different instruments and different methods, all converging on the same answers. The model predicted the precise pattern of hot and cold spots in the afterglow of the Big Bang. When satellites measured that afterglow, the match was nearly perfect. It predicted how many light elements like hydrogen and helium the early universe should have cooked. The measured amounts agree. It predicted how galaxies should be scattered across the sky. The great surveys found exactly those patterns. Imagine a detective novel where a single suspect explains every clue on every page. That was the standard model for 2 decades. It became the framework for essentially all of cosmology, the lens through which every new observation was interpreted. Some researchers began to speak as if the remaining work was simply measuring the model's parameters to more decimal places, and the model told us how everything will end. Run the equations forward and the prediction is stark. Dark energy constant and eternal, keeps stretching space faster and faster. Distant galaxies accelerate beyond our sight, their light unable to outrun the expansion. Star formation sputters out as fuel runs dry. The last stars cool into cinders. The cosmos ends cold, black, and empty, a thin gruel of nothing spreading forever. That forecast, sometimes called the heat death, became part of our culture's story about reality itself. The model's description of the past is supported by mountains of evidence. Its description of the far future rests on one enormous assumption, that dark energy never changes. Every prediction about the end of everything hangs from that single thread. For years, no observation could test the thread. The model seemed finished, polished, complete, but a theory that explains everything has a hidden vulnerability. It only takes one stubborn, unexplainable measurement to put the entire structure on trial. And that measurement arrived in the form of the most important number in cosmology. The expansion rate of the universe, known as the Hubble constant. There are two great ways to measure it. Here is where the trouble starts. The first way looks at the modern universe, the space near us. Astronomers like Riess measure the distances to galaxies and clock how fast they are moving away. Distance and speed together reveal the expansion rate directly. It is the cosmic equivalent of standing by a highway with a radar gun. The second way looks at the ancient universe. Scientists study the afterglow of the Big Bang, that faint radiation released when the cosmos was only 380,000 years old, and measure its patterns with exquisite precision. Then they feed those patterns into the standard model and let the equations run forward like winding a clock from the beginning of time to today. The model then announces what the expansion rate must be now. Two methods, one radar gun aimed at the present, one clock wound from the past. If the standard model is correct, they must agree. They do not agree. This is confirmed observation verified by independent teams around the world. The radar gun method measuring the nearby universe consistently finds the expansion running roughly 9% faster than the wound clock predicts. 9% may sound small. In precision cosmology, it is a canyon. Both camps have sharpened their measurements for years. Instead of converging, the two answers have hardened, each becoming more certain, more precise, and more incompatible with the other. The disagreement grew so persistent that scientists gave it a name, the Hubble tension. When the tension first appeared in the early 2000s, almost everyone expected it to evaporate. Small discrepancies appear in science all the time and usually dissolve when instruments improve. The history of physics is littered with anomalies that faded under closer examination, and nobody wanted to be the researcher who cried revolution over a subtle measuring mistake. Riess himself expected his result to drift back into agreement. The opposite happened. The more data he gathered, the more stubborn the gap became. Meanwhile, the ancient universe measurement made by a satellite mapping, the Big Bang's afterglow, reached a precision so fine that its error bars became razor thin. The gap stood firm between two immovable walls. The standard model is the machine that converts the early universe into a prediction for today. If the prediction fails, one of two things is true. Either one of the measurements hides a subtle flaw that the world's best scientists have somehow missed for a decade, or the machine itself, the standard model of cosmology, is missing a piece of reality. Riess has staked his reputation on the measurements being sound. His confidence comes from the way his side of the measurement is built, a towering structure of interlocking evidence that astronomers call the cosmic distance ladder. You cannot stretch a tape measure across the universe. There is no single instrument that can measure the distance to a galaxy millions of light years away. So astronomers built a chain of overlapping methods where each rung calibrates the one above it. The first rung begins close to home. For nearby stars, astronomers use simple geometry. As Earth circles the Sun, nearby stars appear to shift slightly against the distant background, the same way your finger appears to jump when you view it with one eye and then the other. Measure that tiny shift and trigonometry hands you the distance. This is confirmed rock-solid technique refined for centuries. The second rung uses a gift from the cosmos, a special kind of star called a Cepheid variable. These stars pulse, brightening and dimming in a steady rhythm. The slower a Cepheid pulses, the more luminous it truly is. This relationship was discovered more than a century ago by astronomer Henrietta Leavitt. Compare true brightness to apparent brightness, and the distance falls out, exactly like judging how far away a lighthouse is when you know the wattage of its bulb. Geometry from the first rung calibrates the Cepheids. The Cepheids then reach out to other galaxies millions of light years away. In some of those galaxies, astronomers catch the third rung, exploding stars, the same standard candle supernovae that made Riess famous, detonations so brilliant that at a single one can briefly outshine an entire galaxy of 100 billion stars. The Cepheids calibrate the supernovae. The supernovae then reach across billions of light years deep into the expanding universe, where the expansion rate can be read directly, rung by rung. Doorstep to horizon, the ladder's weakness is obvious. An error on any rung climbs upward and infects everything above it. This is exactly where critics aimed for years. Perhaps the Cepheid measurements were contaminated. Cepheids live in crowded, dusty regions of galaxies, and when telescopes photograph them, nearby stars can blend into the image, subtly corrupting the brightness readings. Astronomers call this crowding. It was the most serious objection on the table, a genuine open question. So Riess and his team did what careful scientists do. They attacked their own ladder. They rebuilt it using different telescopes, different wavelengths of light, different calibration stars. They swapped Cepheids for entirely different stellar rulers and got consistent answers. They hunted for every source of contamination that critics proposed. Year after year, the ladder held and the fast expansion rate refused to budge. Still, one doubt remained, one loophole that no ground telescope and even the mighty Hubble Space Telescope could fully close. Hubble's vision, sharp as it was, could not perfectly separate Cepheids from their crowded stellar neighborhoods in the most distant calibration galaxies. The skeptics had a final refuge, blurry photos. What the ladder needed was an eye sharp enough to end the argument forever. An instrument that could resolve those pulsing stars cleanly, one by one, across intergalactic distances. In late 2021, that eye launched into space. Every cosmologist on Earth understood the same thing. The James Webb Space Telescope was about to deliver a verdict. Now cross to the other side of the argument, because it is every bit as formidable. The rival measurement comes from the oldest light in existence. When the universe was young, it was a glowing fog so hot and dense that light could not travel freely. Around 380,000 years after the Big Bang, the fog cooled enough for atoms to form, and light broke loose in every direction at once. That ancient flash is still traveling. It fills the entire sky tonight, stretched by cosmic expansion into faint microwaves. Scientists call it the cosmic microwave background. This relic light was discovered by accident in the 1960s by two engineers who thought the strange hiss in their antenna might be pigeon droppings. It was the afterglow of creation. Ever since, satellites have photographed this baby picture with rising precision. The most detailed portrait came from a European satellite called Planck. What Planck saw was breathtaking. The afterglow is almost perfectly smooth, yet speckled with faint hot and cold patches, temperature differences smaller than a 100,000th of a degree. Those speckles are the seeds of everything. Each slightly denser patch would later collapse under gravity into galaxies and clusters of galaxies. Your body tonight exists because of one of those ancient ripples. Here is where the Standard Model performs its greatest magic trick. The sizes and patterns of those speckles encode the recipe of the young cosmos. How much ordinary matter it held, how much dark matter, how fast it was expanding. Feed the baby picture into the model's equations. Run the universe forward for nearly 14 billion years, and the model announces what the expansion rate should be today. The precision of this process is astonishing, and its internal consistency has been checked thousands of ways. The prediction comes out low, substantially lower than what Adam Riess measures in the sky around us. Picture what this means. Imagine finding a photograph of a river taken from a mountaintop long ago, so detailed that engineers can calculate exactly how fast the water should be flowing downstream today. Then you walk to the riverbank, drop a leaf in the water, and time it. The leaf races past faster than the photograph allows. You check the photo, flawless. You time the leaf again, faster. Both cannot be right unless something changed the river along the way. That is the Hubble tension in a single picture. The baby picture method carries no crowded star fields, no dust, no ladder of rungs to doubt. Its weakness lies elsewhere. It does not measure today's expansion directly. It predicts it using the Standard Model as the bridge between then and now. The ladder method measures today directly and needs no bridge at all. The two methods fail in opposite ways, which makes the disagreement so diagnostic. If both measurements are clean, the bridge itself is broken. Something in the Standard Model is wrong. For years, the escape hatch was to blame the ladder, those blurry, crowded Cepheids. It was the respectable position, the safe position. Then the sharpest eye ever launched into space opened its golden mirror, aimed it at those exact stars, and the safe position began to dissolve 1 million miles from Earth. A machine the size of a tennis court drifts in permanent shadow, its golden mirror colder than the space between stars. The James Webb Space Telescope is the most powerful eye humanity has ever built, the culmination of more than 20 years of engineering and $10 billion of investment. When it opened in 2022, cosmologists knew it would face a question with the weight of the entire Standard Model behind it. Were the ladder measurements wrong? If the Cepheid measurements were contaminated, the fast expansion rate might be an illusion, the Hubble tension might evaporate, and the Standard Model would be safe. The Webb telescope sees in infrared light with a mirror 6 times larger in area than Hubble's. Where Hubble saw a smeared blob, Webb resolves individual stars, clean and separated, like switching from a foggy window to open air. Adam Riess did what he has always done. He aimed the new instrument directly at the heart of his own life's work, fully prepared to watch it collapse. If the crowding critics were right, Webb's sharper vision would reveal that the Cepheids were systematically brighter than they appeared, the distances would shift, and the tension would dissolve. The observations came back. The verdict was clean. Webb's razor-sharp measurements of hundreds of Cepheids matched the Hubble telescope's measurements almost perfectly. The blur had introduced no meaningful error. The stellar rulers were true. The fast expansion rate stood confirmed. This is verified, published science, checked and rechecked across multiple galaxies. Riess and his colleagues went further, spanning the full range of distances that Hubble had ever observed, replacing every questionable rung of the ladder with Webb's superior vision. The answer refused to move. The nearby universe really is expanding faster than the baby picture predicts, by the same stubborn margin as ever. Feel the shift that happened in that moment. For years, the community's quiet consensus was that the tension would die the way most anomalies die, killed by better data. Instead, the best data ever collected walked into the room and stood beside the anomaly. One of the last respectable escape routes from the crisis closed. Riess put it plainly. With measurement error ruled out at high confidence, the possibility that scientists have misunderstood the universe becomes very real. This was the moment the Hubble tension stopped being a curiosity and became, in the eyes of many physicists, the most important clue in all of cosmology. Conferences that once tucked the topic into afternoon sessions began opening with it. Theorists who had waved it away began publishing frantic explanations. The whisper became a roar. Something is missing from our model of the universe. And yet, even as Webb was closing one escape route, careful observers noticed that the mystery was deepening. The tension in the expansion rate was no longer alone. Other measurements, entirely independent ones, probing entirely different aspects of the cosmos, were quietly drifting away from the standard model's predictions too. Science has a brutal tradition. When a result threatens a beloved theory, the result is presumed guilty until proven innocent. For a full decade, the fast expansion rate lived under that presumption, and Adam Riess spent those years as both defendant and detective, methodically eliminating every accusation against his own measurement. The first accusation was crowding. The Webb telescope executed that suspect completely. Suspect 2, cosmic dust. Dust dims and reddens starlight, which could distort brightness measurements, so astronomers remeasured the ladder in infrared light, which passes through dust like sound through a curtain. The answer held. Suspect 3, the calibration stars themselves. Perhaps Cepheids in distant galaxies differ chemically from those nearby, subtly changing their rhythm. Teams tested for this across galaxies with different chemical compositions. The answer held. Suspect 4, the entire species of calibration star. If Cepheids carried some hidden systematic flaw, replacing them should shift the result. So astronomers rebuilt the ladder using completely different stellar rulers, including a class of red giant stars whose peak brightness is set by well-understood physics. Different stars, different physics, different teams, different telescopes. The answer held. Suspect 5, the supernovae. Different analysis groups using different statistical methods and independent software processed the exploding star data from scratch. The answer held. Suspect 6, human bias itself. Astronomers ran blinded analyses, hiding the final number from themselves until every choice was locked, so no one could steer the result toward a preferred answer. The answer still held. There is even a rung that bypasses starlight entirely, in a technique that borders on the unbelievable yet is confirmed methodology. Astronomers used networks of radio telescopes to watch clouds of water vapor orbiting the giant black holes at the centers of distant galaxies. The geometry of those orbits reveals pure direct distances with no ladder at all. The expansion rate that came back agreed with the fast answer. By the middle of this decade, Riess could state publicly that measurement error had been ruled out with very high confidence. In statistical language, The tension has climbed far beyond the threshold physicists traditionally demand before declaring a discovery. The odds of the discrepancy being a random fluke are now considered vanishingly small, comfortably below 1 in a million by the standard measures used in the field. Imagine a courtroom where a dozen independent witnesses, none of whom know each other, each arriving by a different road, all describe the same suspect. At some point, doubting the witnesses becomes harder than accepting the crime. A minority of respected cosmologists still suspect an unknown, subtle error, some conspiracy of small mistakes aligning in one direction. Science must always hold that door open, but the door has narrowed year after year, and behind it stands a decade of failed attempts to find the flaw. If the measurements are innocent, then the theory is guilty. Once physicists started seriously auditing the standard model itself, they discovered that the expansion crisis was only the beginning of its troubles. Riess has a metaphor he likes for the state of modern cosmology. The standard model resembles an egg with cracks spreading across its shell. One crack might be cosmetic, but cracks have a way of finding each other. The Hubble tension has company, and as Riess's egg metaphor suggests, the cracks are spreading. The second major crack concerns cosmic clumpiness. The baby picture of the universe tells the standard model exactly how lumpy the cosmos should have become by today, how strongly matter should have gathered into clusters and filaments over billions of years. Astronomers test this by measuring a subtle effect called weak gravitational lensing, in which the gravity of invisible matter gently bends the light of galaxies behind it, distorting their shapes by amounts almost too small to detect. Several major surveys mapping millions of galaxies have reported the same curious shortfall. The universe appears slightly smoother, slightly less clumped than the model predicts. The discrepancy is milder than the Hubble tension, and some recent analyses soften it. But notice its direction. Once again, the ancient universe and the modern universe refuse to shake hands. Crack number 3 appeared where no one was even looking. The standard model rests on a bedrock assumption called the cosmological principle, the idea that on the grandest scales, the universe is uniform with no special places and no preferred directions. Yet surveys keep stumbling over structures that seem too vast to exist. Astronomers have mapped colossal arrangements of galaxies and quasars stretching billions of light years, walls and arcs and rings so large that, according to the model, gravity should never have had time to organize them. Each individual claim remains debated, and that trust signal matters. Still, the list of giants keeps growing, and each one strains the assumption of a smooth, uniform cosmos a little further. A fourth set of oddities hides inside the baby picture itself. The afterglow of the Big Bang contains faint anomalies. A strange cold spot far larger than expected, and a subtle hint that one half of the sky differs slightly from the other, as if the universe has a faint axis. Statisticians argue about every one of these features. Any single one could be coincidence. Together, they form a pattern of small embarrassments that the standard model can only shrug at. And then there is the crack that may swallow all the others, the one that strikes at dark energy itself. The model demands that dark energy be a cosmological constant, utterly unchanging across all of time. Every prediction about the fate of the universe depends on that constancy. For 25 years, no instrument could truly test it. Now one can. On the summit of Kitt Peak in Arizona, an aging telescope received a new soul. The dark energy spectroscopic instrument, called DESI, holds 5,000 robotic positioners, each a slender finger of metal gripping a fiber optic cable, each able to swivel and lock onto a single galaxy in seconds. When the dome opens at night, 5,000 galaxies pour their light down 5. 00 fibers simultaneously. Each fiber is positioned with micrometer precision by its own robotic arm, a choreography of engineering that would have been science fiction just a generation ago. 20 minutes later, the robots pivot in a soft mechanical whir, and 5,000 new galaxies take their place. Night after night, the machine drinks the universe. In its first years, it gathered the light of tens of millions of galaxies and quasars, building a three-dimensional map of the cosmos that dwarfs every survey before it, reaching back through 11 billion years of cosmic history. The true prey is dark energy, and the trap uses fossilized sound. Rewind to the universe's fiery youth before atoms formed. Matter and light sloshed together in a dense plasma, and pressure waves, literal sound waves, rippled through that cosmic ocean like rings spreading from raindrops on a pond. When the fog cleared and atoms formed, those ripples froze in place. The universe kept expanding, and the frozen ripples expanded with it, leaving a faint preference for galaxies to sit at one particular separation from each other, a fossil wavelength imprinted across the entire cosmos. Astronomers call these baryon acoustic oscillations, and they are one of the most beautiful confirmed discoveries in modern science. That fossil ripple has a known physical size. It is a ruler forged in the Big Bang, stamped identically across every era of cosmic history. Measure how large the ruler appears at different distances, and you can reconstruct the entire expansion history of the universe epoch by epoch, like counting growth rings in a tree. If dark energy is truly a constant, the expansion history must follow one exact curve. Any deviation at any era means the so-called constant is nothing of the sort. For decades, this test was a dream because no map was large enough. The Desert Instrument made the map. Its scientists ran blinded analyses, concealing the cosmological answers from themselves until every decision was frozen, precisely so that hope and fear could not bend the outcome. At a conference in April 2024, the collaboration unblinded its first year of data and showed the world. The fossil ruler measurements were magnificent, the most precise ever achieved. But the expansion history did not quite follow the sacred curve. The deviation was gentle, tantalizing, hovering at the edge of statistical significance. Interesting, the cautious said, but wait for more data. So the robots kept swiveling, the map kept growing. 2 years later came the second release with triple the galaxies. The results appeared. The anomaly had grown teeth. The data now hints that dark energy, the dominant force in the universe, the engine of cosmic acceleration, may be weakening. The Desert Instrument's expanded map, combined with supernova surveys and the afterglow of the Big Bang, keeps pulling away from the constant dark energy of the Standard Model. The preferred solution describes a dark energy that was stronger in the cosmic past and has been gently fading ever since, as if the accelerator pedal of the universe is slowly easing off. The statistical strength of this result sits in the uncomfortable zone, stronger than a hint, weaker than a confirmed discovery. Depending on which datasets are combined, the significance flickers around the level where physicists start losing sleep, still shy of the gold standard the field demands before declaring victory. Some prominent skeptics argue that quirks in the supernova catalogues could be manufacturing the signal. That debate is genuine and unresolved. But grasp why this particular anomaly is different from every other crack we have surveyed. It offers an explanation. The Hubble tension is a disagreement between the universe's past and its present, a bridge that fails when the Standard Model carries predictions forward through time. Every attempt to fix a measurement has failed. The remaining option was always to fix the bridge, to change some ingredient of the cosmos itself. Dark energy that changes over time is exactly such an ingredient. If the engine of expansion has been evolving, then the model's conversion of the baby picture into a modern expansion rate was using the wrong physics all along. The two clocks might both be honest, ticking inside a universe whose machinery is different from the one in our textbooks. Riess was pleased when the Desert Instruments results emerged. Another tough result for the Standard Model. Another crack finding a partner crack. For a man who spent a decade being told his measurement must be flawed, there is a quiet vindication in watching an entirely independent experiment stumble into the same conclusion. Something is wrong with the model. Now allow yourself to feel the size of what may be shifting. Dark energy makes up roughly 70% of everything that exists. If it is weakening, then the most abundant substance in reality is unstable, and physics has no idea what it is or why it changes. The cosmological constant, Einstein's elegant symbol, would be dethroned after a century. Nobel Prizes were awarded, textbooks were printed, and the fate of the universe was forecast, all assuming a constant that may never have been constant at all. One theorist compared the community's reaction to watching a mountain move, a mountain that everyone had been assured could never move at all. If the force pushing the universe apart is fading, what happens when it fades further? Could it stall? Could it reverse? The Standard Model's cold, empty, forever suddenly has rivals, and some of them end in fire rather than ice. If the Standard Model is broken, someone has to fix it. Theoretical physicists have spent the last several years in a frenzy of invention, generating hundreds of candidate models, tweaked ingredients, added fields, bent equations, searching for anything that can explain all the anomalies at once without breaking something else. Be clear about its status from the start. This is a theory unconfirmed, one candidate among many, but it is a serious candidate crafted by careful people. The proposal goes like this. Alongside matter, light, and ordinary dark energy, the infant universe contained one more ingredient, an extra energy field that behaved like a hidden booster rocket. It switched on briefly in the primordial fire, gave space an additional shove during a narrow window of time, and then decayed away to nothing, vanishing before the universe was even 1,000,000 years old. Why would that tiny episode matter billions of years later? Because of a subtle domino effect. That early shove would have slightly changed how far sound waves could travel through the primordial plasma before the fog cleared. Remember the fossil ripples? The frozen sound waves that serve as a cosmic ruler. Early dark energy would shrink that ruler by a few percent. Shrink the ruler, and every measurement built upon it shifts. Run the correction through the mathematics, and something remarkable happens. The predicted expansion rate rises, climbing toward the fast value that Riess measures in the modern sky. The two clocks begin to agree. The Hubble tension dissolves. One brief flicker of ghost energy at the dawn of time, and the great crisis of cosmology evaporates. It is elegant. It is also in trouble. When theorists adjust the early universe to fix the expansion rate, the change ripples into other predictions. Versions of early dark energy that cure the Hubble tension tend to worsen the clumpiness problem, predicting a universe even lumpier than the smooth one surveys actually observe. Fixing one crack widens another. The afterglow data itself also leaves only a narrow corner where the ghost field can hide. Some physicists find the whole construction contrived, a new fudge factor stacked on old mysteries. Others believe it is the leading clue we possess. The debate rages in journals and conference halls right now, unresolved. And while theorists argue about invisible forces at the dawn of time, a very different school of thought asks a humbler, stranger question. What if the problem is location? What if our entire galaxy, our star, and every world we have ever known sit inside one of the emptiest regions of the nearby universe, a cosmic cavity so vast that light needs roughly 2 billion years to cross it? The idea sounds like pure fantasy. It is a genuine scientific proposal, published, debated, and taken seriously by a growing minority of astronomers. The evidence begins with simple counting. When astronomers survey the galaxies surrounding our own across enormous distances, several independent studies report a shortfall. Our cosmic neighborhood appears noticeably less crowded than the universal average, perhaps a fifth less dense, as if we occupy a thinned-out bubble in the cosmic web. Researchers call it the local void, and its existence, while still contested, is supported by galaxy counts across multiple wavelengths of light. If it is real, the consequences for our crisis are electric. Gravity pulls matter toward crowded regions. If we live inside an underdense bubble, the denser walls surrounding the void are constantly tugging galaxies outward away from us, adding an extra outward drift on top of the true cosmic expansion. Astronomers inside the void, measuring the recession of nearby galaxies, would clock an expansion rate faster than the genuine universal value. Their local speedometer would read high through no fault of their instruments. The Hubble tension would then be an illusion of address, a trick of living in the wrong neighborhood. Recent studies have strengthened the case, showing that fossil sound wave measurements combined with low galaxy data actually favor a void model over a perfectly uniform cosmos. In some analyses, the proposal has climbed from fringe curiosity to respectable contender. But it faces a formidable obstacle, and Riess himself wields it. His team measures the expansion using supernovae spread across a colossal range of distances, many of them far beyond any plausible edge of the void. If the fast expansion were a local illusion, the measured rate should drop back to the global value once the ladder climbs past the void's walls. According to his analyses, it does not drop. The fast rate persists deep into the cosmos, far beyond where the bubble's influence should fade. Void skeptics also note that a cavity large and deep enough to explain the entire tension would itself violate the standard model, which predicts such giant fluctuations should be vanishingly rare. The trap closes from both directions. If the void is too small, it cannot explain the tension. If it is large enough to explain the tension, its very existence breaks the model anyway. Heads or tails, the standard picture loses something. The void question opens a darker door. The model's foundation assumes the universe on grand scales looks the same everywhere and in every direction. Astronomers are now testing that sacred assumption directly. Beneath every equation of the standard model lies a promise so basic it is rarely spoken aloud. The universe has no special places and no special directions. Zoom out far enough, the promise goes, and the cosmos becomes perfectly uniform, the same soup in every direction like fog with no landmarks. Cosmologists call this the cosmological principle, and it is the bedrock beneath everything else. Without it, the model's equations cannot even be written down. Testing it is among the most important tasks in science. One elegant test involves our own motion. Confirmed measurements show our galaxy is streaming through space, and this motion imprints a signature on the sky. In the direction we are moving, the afterglow of the Big Bang appears very slightly warmer, and behind us slightly cooler, like the bow wave of a moving boat. Simple physics demands a matching signature elsewhere. If we look at distant galaxies and quasars, ancient beacons scattered across the whole sky, their counts should show the same tilt. Slightly more of them piled up ahead of our motion, slightly fewer behind. Both patterns should point the same way with the same strength. Researchers counted using catalogues of millions of distant quasars and radio galaxies. The direction matched. The strength did not. Several analyses report the tilt in the distant galaxy counts to be roughly twice as strong as our measured motion allows. A mismatch, some teams calculate, has less than a 1 in a million probability of being chance. If the excess tilt is real, the implications are seismic. It would mean the universe itself is unbalanced, its matter leaning in one direction on the grandest scales, in direct violation of the founding promise. Other strange compass needles point in worrying directions too. Studies of galaxy clusters have tested whether cosmic expansion runs at the same speed across the sky. Some find hints that it may not, as if the universe stretches faster along one axis than another. Surveys of quasar polarization report curious alignments spanning billions of light years. Even the rotation directions of galaxies have been claimed controversially to favor one-handedness in certain regions of sky. Each claim individually faces vigorous challenge, and many may dissolve under better data. Science demands that honesty. Yet notice what has changed in the field's mood. Questions once considered settled are being reopened one by one. The reopening itself tells you how deep the confidence crisis runs. A lopsided universe would mean that both clocks were built on a false floor, and the Hubble tension might be merely the loudest symptom of a far stranger disease. When the James Webb Space Telescope opened its golden eye, one of its first assignments was pure time travel. Webb was built to catch the light of the very first galaxies, structures shining barely a few 100 million years after the Big Bang, the cosmic equivalent of baby photographs. The standard model had firm expectations for what those photographs would show. Galaxy formation in the model is slow cooking. Small clumps of dark matter gather gas, ignite modest sprinkles of stars, then merge and grow across billions of years into giants like our own Milky Way. The dawn era should therefore contain only faint, scrawny, half-formed smudges. Webb aimed, exposed, and sent home its first deep images. Astronomers opened the files and found the nursery full of adults. This is confirmed observation replicated across multiple surveys. Webb revealed galaxies in the universe's first several 100 million years that are shockingly bright, surprisingly massive, and in some cases startlingly mature, with orderly disks and hints of old stellar populations. Early candidates were so extreme that headlines declared cosmology broken. Careful follow-up trimmed the wildest claims, and that correction matters. Some record breakers turned out to be closer than they appeared, their distances misjudged. Yet, after all the pruning, a stubborn core of confirmed impossible objects remains. Galaxies too luminous, too numerous, and too developed for their cosmic age, appearing several times more abundant at the highest distances than the standard recipe predicts. One confirmed system observed as it was barely 700 million years after the beginning already resembles a settled spiral. Another shows signatures of stars that look old in a universe that had barely begun. Imagine an archaeologist digging into the deepest, most ancient layer of an excavation, expecting crude stone tools and instead unearthing a functioning wristwatch. That is the flavor of what Webb keeps finding at the bottom of time. What could explain it? The sober possibilities come first. Perhaps early star formation was far more efficient than assumed, converting gas into stars in furious bursts. Perhaps the first stars were strange titans, brighter per pound than any stars today, making young galaxies look more massive than they are. These explanations require rewriting textbook astrophysics, but they spare the standard model's foundations. The radical possibilities come next. Some cosmologists propose that structure began growing earlier or faster than the model allows, which would point toward new physics in the dark sector, perhaps even connecting to the evolving dark energy hinted at by the desert instrument. A few theorists argue that tension eases if the universe's expansion history differs from the standard timeline, the same suspicion haunting the Hubble tension from another direction. Notice that convergence because it is the quiet theme of this entire story. Independent instruments, independent methods, independent teams, all scraping against the same wall. The early universe, as described by the standard model, keeps failing to produce the present universe we actually observe. Each anomaly alone can be argued away. Together, they begin to rhyme. There is an old joke among physicists, usually credited to Max Planck, that science progresses one funeral at a time. New truths win only when the defenders of old truths retire from the field. Cosmology today is living that joke. Consider the position of the standard model's senior architects. Many spent 40 years constructing it, measurement by measurement, paper by paper. Their textbooks teach it. Their students' careers depend on techniques built inside it. Their life's meaning is braided into its equations. Now imagine a colleague standing at a conference podium presenting data, suggesting the great edifice rests on a floor. Adam Riess has described the sociology bluntly in interviews. He speaks of an establishment reluctant to engage, of theorists who dismiss conflicting data rather than confront it, of what he views as a clique of senior figures waving away results that refuse to fit. When he reaches out for help interpreting his measurements, he has said the responses often disappoint him. Prominent scientists have publicly cautioned that Riess may be getting ahead of the evidence. One leading figure described him as arguing loudly and fiercely with anyone who disagrees. Skeptics point out correctly that most anomalies in the history of physics eventually dissolved. Extraordinary claims require extraordinary evidence, and defending a successful model against premature revolution is itself good science. Both instincts, the rebels and the guardians, are necessary. Science advances through their collision. The collision is getting loud. Conference sessions crackle with tension. Younger cosmologists, sensing opportunity, flood into the gap with heretical models. Senior figures counter with sharpened defenses of the standard picture. Riess himself, once besieged after his Nobel win by every committee and panel seeking his name, deliberately turned away from the administrator's path. He chose to remain a frontline investigator. There is a confession Riess has made that stops people cold. Reflecting on years of gathering flawless measurements that no theory can explain, he has said that he sometimes feels he is merely providing clues and killing time, waiting for the next Einstein to come along. One of the most accomplished physicists alive, a Nobel laureate at the peak of his powers, openly suggesting that the resolution of cosmology's crisis may require a category of genius that does not currently exist on Earth. It sounds like despair. It is actually a precise historical diagnosis. Remember what happened the last time physics stood in this exact spot. At the closing years of the 1800s, physics seemed essentially complete. Newton's mechanics explained motion. Maxwell's equations explained light. Prominent voices declared that only details remained, measurements to another decimal place. Yet a few small anomalies refused to behave. The orbit of Mercury drifted by a whisper each century, defying Newton. Experiments could find no trace of the ether that light supposedly travelled through. Hot objects glowed with colours that theory could not reproduce. Small cracks, annoying cracks. Cracks most experts expected to dissolve with better data. Those cracks were the 20th century knocking. Resolving Mercury's drift required tearing down Newton's gravity and replacing it with curved space-time. Explaining the glow required quantum mechanics, a theory so strange its own founders recoiled from it. The anomalies had seemed minor because everyone assumed the existing framework was fundamentally sound. It was not. Riess believes cosmology may be standing before cracks of the same kind. The Hubble tension, the impossible galaxies at the dawn of time, the restless dark energy that may be fading, the lopsided sky. Perhaps each has a mundane fix. Or perhaps like Mercury's whisper, they are the accent of an undiscovered language, the first audible words of a deeper theory that will make our current model look like a childhood sketch. While the world waits for its genius, a handful of living theorists refuse to wait. Some have begun questioning ideas so fundamental that even rebels flinch. A few are now asking whether the founding observation of all cosmology, the redshift of galaxies, means what we have believed for 100 years. For a century, the answer has been expansion. Space itself stretches as light crosses it, and the light stretches along with it like a wave drawn on a rubber band being pulled. Accept that interpretation and everything follows. The Big Bang, the cosmic timeline, dark energy. Question the interpretation and the entire cathedral trembles. A more sophisticated version called timescape cosmology strikes at an assumption almost nobody thinks to question: time itself. Einstein taught and experiments confirm that clocks tick at different rates depending on gravity. A clock inside a dense region of matter runs slower than a clock drifting in a vast empty void. The universe is a foamy web of dense galaxy walls wrapped around enormous empty bubbles. The Standard Model smooths this froth away, treating the cosmos as uniform and applying one universal clock everywhere. Timescape refuses to smooth. In this framework, billions of years of accumulated clock differences between voids and walls add up to something astonishing. The voids, aging faster, expand more than the crowded regions. Observers like us, living inside a galaxy wall, misread that patchwork of mismatched clocks as a mysterious acceleration. Dark energy in timescape cosmology is an accounting error. There is no hidden force. The recent analyses of large supernova catalogues have delivered a jolt, with some studies reporting that timescape fits the data as well as the Standard Model, and by certain statistical measures, slightly better. Most cosmologists still back the Standard framework. Yet the fact that a dark energy-free universe remains statistically competitive is itself a stunning indictment of how much remains unknown. The age of the universe is also hostage to the theory now under siege. The confident number of 13.8 billion years that appears in textbooks, documentaries, and museum exhibits around the world is not a direct measurement. It is a calculation, and the calculation runs through the Standard Model. Feed the model the afterglow of the Big Bang. Assume the standard ingredients, including a perfectly constant dark energy, and the equations wind backward to the beginning announcing the elapsed time. Change the model and the birth date changes with it. A faster expansion taken at face value and run backward points toward a younger universe, shaving away perhaps 1 billion years. An evolving dark energy would bend the answer in ways that depend on exactly how the mysterious engine has changed over time. A lopsided universe or a timescape cosmos with its patchwork clocks would scramble the question even further, because in such a cosmos different regions would have aged by different amounts, and the universe would have no single age at all. There is a wonderfully human way to check cosmic ages. You cannot be younger than your own children. Astronomers hunt for the oldest stars, knowing the universe must be older than every star it contains. In the 1990s, before dark energy's discovery, this test went spectacularly wrong. The best cosmological models of that era, lacking dark energy, calculated a universe younger than the ancient stars in globular clusters, tight swarms of stars orbiting our galaxy like fireflies around a lantern, children older than their mother. The paradox screamed that something was missing from the model. Something was. When dark energy entered the equations, the calculated age stretched comfortably beyond the stellar ages, and the paradox dissolved. An age crisis was the early warning that the cosmic recipe was incomplete. Today, ancient globular clusters dated through the physics of how stars burn and fade yield ages that press snugly against the cosmic limit. The margin between the oldest stars and the age of everything remains uncomfortably thin. There is no confirmed contradiction tonight, but the fit is tight enough that a modest revision of the expansion history, exactly the kind of revision now being debated, could reopen the old paradox in a heartbeat. If the past is negotiable, the future is wide open. The same broken assumptions that cloud the universe's age also wrote its obituary. For the last 25 years, science believed it finally knew how the story ends. The Standard Model, with its constant dark energy, delivers a verdict of ice. Expansion accelerates forever. Distant galaxies slip one by one beyond the reach of light, their images fading like ships over a horizon. Star formation exhausts its fuel. The last stars gutter out over spans of time so vast that the universe's current age is a rounding error. Even matter itself may decay, leaving a cold, dark, dilute nothing expanding pointlessly forever. Scientists call it the heat death. That obituary was written with one crucial assumption inked into every line: dark energy never changes. Erase that assumption as the Desert Instruments data now urges us to consider, and the ending of the universe becomes an open question for the first time in a generation. Path 1, dark energy weakens and settles gently to zero. Acceleration fades. Expansion continues, coasting forever, slowing but never stopping. The far future still grows cold and dark, a quieter version of the old ending. Path 2, dark energy fades to nothing and keeps falling, turning negative, transforming from a push into a pull. This is the path that has cosmologists whispering, because the Desert Instruments' favored models flirt with exactly this behavior. A negative dark energy would join forces with gravity. Expansion would slow, halt, and reverse. Galaxies that spent billions of years fleeing one another would turn and begin the long fall home. Path 3 is stranger still. Some theories treat dark energy as a field slowly rolling downhill toward a new configuration, a process that could quietly rewrite the laws of physics themselves as it settles, changing the rules inside every atom. And there remains a fourth path, the old nightmare in the other direction. If dark energy were instead to strengthen without limit, it would eventually tear apart galaxies, stars, planets, and finally atoms themselves in a final shredding instant that physicists call the Big Rip. Current data has cooled on this scenario, bending toward weakening rather than strengthening. But the door is not fully closed. The most discussed alternative ending deserves its own chapter. Of all the endings physics has ever imagined, none carries the mythic weight of the Big Crunch. It is the ending as mirror image, a universe born in fire, returning to fire, the entire story of existence running in reverse until everything that ever was crushes back into a single point. For decades, this ending was considered ruled out. Dark energy's discovery seemed to slam the door, a cosmos accelerating outward, driven by a constant eternal push, can never turn around. The crunch was filed away as a museum piece, a retired apocalypse. The Desert Instruments data has quietly taken it back off the shelf. If dark energy is weakening, the natural question is where the weakening stops. Some theoretical models explore scenarios where the fading force crosses zero and turns negative, becoming an attractive pull woven into space itself. In such a universe, the fate is sealed with mathematical certainty. Expansion slows. Somewhere in the deep future, it stops entirely. A moment of perfect cosmic stillness, the high watermark of space. Then the fall begins. Recent theoretical studies fitting the new dark energy data have published tentative timelines. In some of these models, the turnaround arrives roughly 10 billion years from now, with the final collapse landing perhaps 20 billion years later, giving the universe a total lifespan of a few tens of billions of years. Our cosmos in this telling is already middle-aged. What would the long fall actually look like through human eyes? Assuming any still existed to watch, for eons nothing would seem wrong. Galaxies would simply notice their distant neighbors growing closer instead of farther, blue shift replacing red shift across the sky. The afterglow of the Big Bang, stretched thin and cold by expansion, would begin compressing back toward warmth, the sky itself slowly heating like an oven with the door closed. In the final billions of years, galaxies merge in cascading collisions. In the final millions, the background sky glows hotter than boiling water, then hotter than any furnace, cooking planets sterile regardless of their stars. Space fills with a rising ocean of radiation. Stars dissolve into the glare. Finally, matter itself surrenders, atoms crushed back into the primordial plasma from which they came, and the universe closes its own parentheses. Some theorists cannot resist the next thought. If a crunch compresses everything back to unimaginable density, could it trigger a new Big Bang, a bounce? A fresh universe rising from the ashes of ours? Cyclic cosmologies, universes breathing in and out across the endless ages, remain speculative in the fullest sense. Nobody knows if the crunch is coming. The dark energy hints must first survive the coming flood of data. Extrapolating trillions of years from a few decades of measurement is heroic guesswork. But the mere fact that serious journals now publish collapsed timelines again after a quarter century of confident eternal expansion tells you how thoroughly the old certainties have dissolved. An army of new machines is coming online around the world and above it, aimed directly at the mysteries we have traveled through. This is confirmed, funded hardware reality, and the next several years of data will likely decide the standard model's fate. Begin on a mountaintop in Chile, where the Vera Rubin Observatory has opened its extraordinary eye. Its camera is the largest ever built for astronomy, the size of a small car with a resolution so vast that displaying a single image at full detail would require hundreds of ultra-high definition television screens. Every few nights it photographs the entire southern sky, and it will repeat that scan over and over for a decade, producing a flickering movie of the universe. It is expected to discover millions of supernovae, dwarfing the few thousand that anchored all previous expansion measurements. Where Riess built his ladder from precious handfuls of exploding stars, Rubin will deliver an avalanche. In orbit, the fleet grows. A European mission called Euclid is already mapping billions of galaxies across a third of the sky, measuring the subtle distortions of gravitational lensing to weigh the universe's clumpiness. Soon it will be joined by the Nancy Grace Roman Space Telescope, an American observatory with a mirror the size of Hubble's and a field of view 100 times wider, purpose-built to hunt supernovae and trace the fossil sound waves deep into cosmic history. Roman will effectively rebuild the distance ladder from space with precision designed to make the Hubble tension impossible to hide or dismiss. On the ground, new microwave observatories in Chile's high desert are rephotographing the baby picture of the universe with sharper eyes than the satellite that defined the ancient measurement. And DESI keeps swiveling its army of robotic fingers, feeding its dark energy measurements toward the decisive threshold. Every major escape route from the crisis is being sealed by an independent machine. If the supernova catalogues hide a subtle flaw, Rubin's millions of explosions will expose it. If the fossil ruler is misread, Roman and DESI will collide over it. If the afterglow analysis leans on an error, the new microwave eyes will find it. If all the instruments confirm the anomalies, the standard model will stand convicted by a jury it cannot recuse. The scientists themselves speak of the coming years the way sailors speak of an approaching storm front, with a mix of dread and exhilaration. Careers will rise and fall on what these machines report. Riess has called it an exciting time, precisely because the field is stuck with more data coming. The one cure science can always count on. Within perhaps 5 to 10 years, the weakening of dark energy will be confirmed or executed. The Hubble tension will be explained or enthroned. There is a genuine possibility that people alive tonight will witness the replacement of humanity's model of the universe. Every scientific model in history has been wrong in the honest sense of incomplete. Newton's gravity ruled physics for 2 centuries, guiding ships and predicting planets, and it is wrong, beautifully, usefully wrong, failing at high speeds and strong gravity. Einstein's relativity corrected it, and relativity itself famously breaks inside black holes. The atom of high school diagrams, electrons circling like planets, is wrong to a cartoon of the quantum truth. Science has never offered final answers. It offers ever better approximations, each wrapped around the last like tree rings. The standard model of cosmology will someday join that noble list of fruitful errors, whether this decade or in a century. When it does, nothing about the universe will have changed. The galaxies will not move differently. Only the map will improve, redrawn to match a territory that was always stranger than the mapmakers knew. The cracks in the standard model were not exposed by its enemies. They were exposed by its builders. Adam Riess, the man whose discovery completed the model, spent a decade constructing the measurements now threatening it. When the anomaly appeared, he sharpened it instead of burying it. The DESI scientists blinded their own analysis so their hopes could not touch the result, then published numbers that undermine the very framework their careers rest upon. Consider how rare that behavior is in human institutions. Governments bury inconvenient findings. Corporations spin them. Science at its best does the opposite, building its entire machinery around the hunt for its own mistakes, rewarding the researcher who breaks the consensus with its highest honors. The crisis in cosmology is that machinery working loudly and in public. There is a personal lesson folded inside the cosmic one. Every one of us carries a standard model of our own life, assumptions about how things work, about what is possible, about how the story ends. And life, like the universe, keeps delivering anomalies, stubborn little facts that refuse to fit the model. The human temptation is always the same: dismiss the data, protect the theory. Wisdom in science and in living runs the other way. The anomaly is not the enemy. The anomaly is information, the universe whispering that reality is richer than your current map. The people who grow like the science that progresses are the ones who lean toward the crack instead of looking away. So when you hear that cosmology is in crisis, hear it correctly. A crisis in science is a feast of clues, the moment before understanding leaps forward. The 1920s gave us an expanding universe. The 1990s gave us dark energy. The coming decade may give us something grander still. If Adam Riess is right, then the true universe is one we have never actually met. A Nobel laureate who found the cracks in his own masterpiece. Two flawless clocks that tell different times. A golden-eyed telescope sent to end an argument and instead certified a mystery. A desert machine drinking galaxies by the thousands, catching hints that the engine of the cosmos is easing off. Galaxies grown impossibly mature at the dawn of time. A sky that may be faintly tilted. A cosmic birth date written in pencil. Endings of ice and fire and a long fall home all return to the table after a generation of certainty. The standard model still fits an astonishing range of evidence, and it may yet survive, patched and humbled. The anomalies may fade one by one, as anomalies often do, or they may sharpen into the outline of a new physics, a deeper theory waiting for its Einstein. The next few years of data will begin to tell. That uncertainty is real, and science would be poorer if we pretended otherwise. But something has already changed forever in the minds of the people who study the sky. The confidence of a completed cosmology is gone. In its place is something older and better, the wide-open wonder of a frontier. For the first time in decades, cosmologists genuinely do not know what the universe is mostly made of, how fast it is stretching, how old it is, or how it ends. Every one of those questions, questions that seemed settled when you were younger, is open again tonight. We are a species of storytellers perched on a small, warm world circling one ordinary star among hundreds of billions in one galaxy among trillions. With nothing but patience, mathematics, and mirrors of polished glass, we read the birth certificate of the cosmos and clocked its racing heart. When our two answers disagreed, we did not hide the disagreement or pretend it away. We did not tear down the scientists who found the crack. We built greater mirrors and aimed them at the mystery. The universe turned out to be stranger than our best story about it. And somewhere out there, woven into the dark energy and the silent voids and the light of the first galaxies, the true story is waiting, patient as starlight, for minds curious enough to find it. Perhaps the mind that finally reads it is asleep somewhere on Earth tonight, a child who has not yet seen their first telescope. Perhaps the answer will arrive in your lifetime. Until then, the sky does what it has always done. The galaxies drift. The ancient light falls softly on our small world. The mystery keeps its vigil overhead, asking nothing of you at all tonight except rest. The questions can stay with the stars where they belong until morning. The universe, whatever it truly is, will still be there when you wake.